All right, today we're going to deconstruct the 2020 paper that introduced the world to GPT-3. And this wasn't just about building a bigger AI. It was about a really radical idea. What if a model could learn a new skill on the fly just by seeing a few examples without any retraining at all? This single idea didn't just move the goalposts, it changed the entire game.
So to really get why this paper was such a big deal, let's just start with a simple question. Think about the last time you learned something new, maybe a board game or a simple recipe. How much information did you really need before you could just jump in and try it?
You know, we humans are pretty amazing learning machines. Give us a few examples, a quick rundown of the rules, and we can usually figure things out. But before this paper, AI was stuck in this much slower, more painful learning cycle. For every single new task, it had to be spoon-fed thousands upon thousands of perfectly labeled examples. This wasn't just inefficient, it was a fundamental roadblock holding AI back.
Okay, so here's how we're going to break this all down. We'll start with the problem they were trying to solve, what we'll call the fine-tuning trap. Then we'll dive into their wild solution, the absolute powerhouse they built to test it, the incredible results they got, and finally, what it all means for where AI is heading.
All right, let's get into the weeds a bit. Before GPT-3 came along, if you wanted an AI model to learn a new trick, the playbook basically had one main strategy: fine-tuning. Now, this process was powerful, no doubt about it, but it was also super restrictive. It's kind of like teaching a brilliant student only one single subject, and that's all they can ever do.
The whole idea was pretty straightforward. You'd start with a big model that's already been trained on a ton of text. Then, for every new job you had for it, like translating French or answering trivia, you had to retrain it all over again on thousands of new specific examples. This process literally changes the model's internal wiring, its parameters or weights, to hard-code it into being a specialist for that one single job.
And you can kind of see here, it's a very deliberate step-by-step process. You feed the model an example, it guesses, you correct it, and you nudge its internal weights just a little bit in the right direction using something called a gradient update. Now repeat that thousands and thousands of times. You end up with a world-class expert, but an expert with total tunnel vision. It can only do that one thing.
So yeah, this was a huge bottleneck. Can you imagine having to find a giant new data set and run a super expensive training process for every single thing you wanted an AI to do? It made it incredibly hard to apply these models to the millions of different tasks that we humans handle so easily. It just wasn't how we learn.
So, all of this led the OpenAI researchers to ask a really wild question. What if, they thought, a model could get so good at understanding the patterns of language that it could learn a brand new skill on the spot, at the exact moment you ask it to, with zero retraining whatsoever?
They called this in-context learning. You can think of it as the model learning how to learn. By reading so much diverse text, it's not just memorizing facts, it's developing a deep intuition for patterns. So when you show it a prompt with a few examples of a new task, it just uses its general knowledge to spot the pattern and continue it. No weight updates, no retraining. Just thinking.
And this slide just lays it all out perfectly. Over on the right, you've got the old way, that slow, methodical grind of gradient updates for every single task. But on the left, you've got the new idea. There are no gradient updates. The model's brain is totally frozen. The entire task is defined purely by the text you give it in the prompt, right then and there. To really put this to the test, the researchers set up 3 different experiments. First was zero shot, where you just tell the model what to do. Then one shot, where you give it one single example. And finally, few shot, where you give it a handful of demonstrations. This let them see really clearly how much better the model got with just a little more context.
So, what was the secret to unlocking this amazing new ability? It wasn't a fancy new algorithm. It wasn't some crazy new architecture. Nope. It was a massive, almost insane bet on one single thing: scale. Just pure, mind-boggling scale.
The model they built to test this idea was GPT-3, and its defining feature was its size: 175 billion parameters. To give you some perspective, that was over 10 times larger than any other dense language model that existed before it. Each parameter is like a little tunable knob that helps the model find patterns, and GPT-3 had a ridiculous number of them to play with. And here's the thing that's really key to understand. GPT-3's underlying blueprint, the transformer architecture, wasn't new. It was the same one used by its little brother, GPT-2. Its one job, its entire purpose in life, is to read some text and predict the very next word. That's it. The magic wasn't in some complex new design, but in the incredible abilities that emerge from doing that one simple thing at a massive scale. Okay, so at the very heart of the transformer is this formula for attention. Now, don't worry, we're not going to do a deep dive into the math, but let's just get the basic idea. For every word it's looking at, the model creates a query, a key, and a value. Think of the query as the current word asking, hey, who else in this sentence is important to me? It then compares its query to the key of every other word. The key is like a little sign that says, here's what I'm about. When a query and a key match up well, they get a high score. Those scores are then used to create a weighted mix of all the values, which is the actual substance of the words. It's basically a super sophisticated way for every word to decide which other words to pay the most attention to. Now, to train a beast like this, you need an insane amount of data. We're talking nearly 500 billion tokens. Most of it, about 60%, came from a filtered snapshot of the public web called Common Crawl. But to make sure it was high quality, they mixed in a curated web text dataset, 2 huge collections of books, and the entire English Wikipedia.
Okay, so they built this monster model. They fed it a huge chunk of the internet. The billion-dollar question was, did the bet on scale actually work? Did it unlock this new kind of learning? Well, the proof was in the pudding. Let's look at the results.
And boom, this chart right here basically proves the entire paper's point. It shows performance across a whole bunch of different tasks. As the model size gets bigger, performance goes up for everyone. But just look at that orange line, diffuse shot performance. See how its slope is steeper? This showed that bigger models don't just get better, they get way better at learning from just a few examples. Scale wasn't just making it smarter, it was teaching it how to learn.
Let's take a specific example. This is for answering trivia questions. The biggest GPT-3 model, just by seeing a few examples in the prompt, actually beat the state-of-the-art model at the time. And remember, that other model was specifically fine-tuned on thousands and thousands of trivia questions. GPT-3 did it cold, just by recalling facts that it stored away in its parameters. Incredible.
Okay, but this is where things get really interesting. The paper discovered these emergent abilities, skills the model was never taught that just sort of appeared at the largest scale. Look at this chart for arithmetic. The smaller models? Totally clueless, just guessing randomly. But then the biggest model suddenly just gets it. It nails 2-digit addition almost perfectly and even does pretty well with 5-digit problems. This was huge. It meant the model wasn't just a fancy parrot, it was starting to reason. And it wasn't just about numbers. The model also tackled SAT analogies, which is a classic test of abstract reasoning. And again, look at that jump. The largest model's performance shoots way up, hitting over 65% accuracy. This showed that scaling up didn't just add more knowledge, it created more flexible, abstract problem-solving skills.
And then, of course, there was the thing that made all the headlines, its ability to write. The model's text was so good that in one study, they had people try to tell the difference between a news article written by a human and one from GPT-3. The result? People were only right 52% of the time. That's basically a coin flip. They couldn't tell the difference.
But, to their credit, the authors didn't just take a victory lap. They were actually really honest about the model's flaws and spent a lot of time thinking about the bigger impact of what they'd created.
The legacy of this paper is just massive. It pretty much kicked off the whole era of large language models, or LLMs. It proved that scale wasn't just a nice-to-have. It was the secret sauce for unlocking new abilities. And it made few-shot learning a common practice. But it also pointed out real weaknesses, like problems with long-form coherence and certain kinds of reasoning, challenges that researchers are still tackling today.
And that leaves us with one final, kind of mind-bending thought. The main idea of this paper, that performance just keeps getting better with more scale, has pretty much held true. So it makes you wonder, if the jump to 175 billion parameters unlocked things like on-the-fly arithmetic and abstract reasoning, what new, unimaginable skills are just waiting to pop into existence at the next level? A trillion parameters? Or even more? That is the question this paper left for all of us to answer.